Thank you very much. Uh, uh, my presentation is an experiment and a simulation study on fracture toughness of fiber reinforced concrete. I'm the Chen, the last one. We from the Tianjin University of China. The presentation includes four parts: background, experiment, and simulation, and then prediction and conclusions. So as you know, the carbon fiber reinforced composites are widely used in industry. There are many kind of the fiber layer method, but for unidirectional fiber reinforced composite, we call it UDFICs, have superior performance in the fiber direction. So in unidirectional fiber reinforced composite have attracted excessive attention. And crack initiation and propagation are inevitable in the process of manufacture and application, such as the common defects are inclusion, porosity, recall, delamination, debonding, magic crack, fiber dislocation, and the fiber fracture. The different relative position of crack and fiber will lead to different fracture behavior, which will affect the fracture performance and the failure mode. That's to say, there are longitudinal interlaminar, longitudinal translaminar, transverse interlaminar, and transverse translaminar, different kind of cracking direction. So it's important to study the fracture behavior of reinforced composite and different orientations, especially to achieve accurate prediction. So this study includes three parts. Fracture. The first one, the fracture tester, is a different orientation specimen. As you see, the fiber is the vertical direction. And the second, for failure analysis, we use the DIC, observed crack tip deformation, and also by OM and SEM for microsurface. And the third part use the numerical simulation and prediction. We developed one and two mixed mode trilinear cohesive zone model and predicted the tensile curve. And this experiment, we use the specimen ESET specimen. We cut the specimen with a different direction, right? With the 0, 15, 13, 45, 60, and 70, and 90 degree. 1, 2, 3. Yeah, 7. Only 7. We have 7 specimens, same kind of specimens. And the carbon fiber reinforced epoxy laminate is like this, the material. So we study the specimen is cut in the TD and the FD plane with a 5 or 7 orientation. And the experiment is conducted on the MTS test machine with the displacement control 0.05 millimeter per minute, and use the DIC system to record the crack initiation angle, growth path, and capturing full field displacement. That is test results, for the CMOD and the force curve, we can see before the crack initiation, the curve is almost linear for all the specimens, and we measure the critical energy release rate for the GC is different with crack orientation, is increased with angle. The GC is measured by area method for calculating fracture toughness. So the stiffness and peak load increase significantly with the increase of angle. The fracture toughness increase with the angle and reach the maximum at the 19 degrees. The maximum, this DIC results, we can see the strain is related with the angle. The maximum side strain increase with angle, which can be used to quantify the fracture toughness. So we fitted this equation. For micro fracture analysis, we observed 0 and 30 degree, 60 degree, and 9 degree by SEM micrograph. The dominant failure mode shifted from the interface debonding and matrix cracking at low angle to fiber fracture and pull out at high angles. The transition is primarily driven by the increasing shear stress component, which promotes a rougher, more complex fracture morphology. So, and then enhanced toughness we can observe for the specimen. For simulation and prediction, normally we use people use the bilinear traction separation law in the cohesive zone model. As you know, this is very simple, but fails to capture progressive damage mechanism like fiber bridging. So trilinear or polylinear traction separation law was employed. It allows for independent control of the energy dissipation in each stage, leading to highly accurate prediction of fracture toughness and low displacement response. So this is a 2-and-1 mixed mode trilinear cohesive zone model. This is the equation for this model. Okay, yeah. And we use the Upq's software. We combine the user subroutine, and we determine the material content by mode 1 and mode 2, and get all the material constants, and then we simulate the force and the CMOD curves for 0, 30 degree, 45 degree, 60 degree, and 9 degree. We only choose 5 specimens, and we got this simulation for the force and the CMOD curves, and the area is very small. So this the DIC and the FEM, and so it's very similar the results. So So it means this method is successful to simulate this kind of material force and the same MOD curves. And for fracture performance prediction, we find the material constant eta 1 and eta 2 in the model. The eta 2 is for the mode 2 is almost constant, but eta 1 is depend on the different degree. So it's a curve. So we fit the eta 1 with the angle to get the equation is one. And then we use this model and also all the material constant to predict the 15-degree and 75-degree examples. The simulation, so it's very good, and the error is less than 2%. So that's a conclusion there. I have time? Okay, fair. So the first one, the fracture toughness increased significantly with fiber orientation angle up to 4 times. And a strong correlation exists between fracture toughness and maximal tensile strength. At orientation 0 degree, failure is dominated by interface debonding and matrix cracking. As angle increase, failure shifts to matrix shear failure, fiber breakage, and fiber pull-out. Normal 1 and 2 mixed mode trilinear cohesive zone model was developed in this study. It can accurately predict load CMOD curves, corrective strain field, and fracture toughness. Thank you very much.